Okay, now in this video I shall explain the concept of an equivalence class, assuming that you already know the definition of an equivalence relation. Now suppose an equivalence relation R, this is an equivalence relation, is defined on a set A. Then a very interesting thing happens. Now, what happens is this equivalence relation R divides the set A into some subsets or compartments, you can say, some subsets which are mutually disjoint and exhaustive. So what happens is the set A is divided into some mutually disjoint and exhaustive subsets. Now two terms here, they are important. One is mutually disjoint and the other is exhaustive. Let us see what they actually mean. So suppose this is my set A on which the relation R is defined. So this is set A. So if R is an equivalence relation, then what will happen is this set will be divided into some compartments. So let us denote these compartments like this. So let us name them as A1, A2, A3, ... and AN. So the set A has been divided into these compartments A1, A2, A3, ... AN. Now they are all mutually disjoint. Now what does that mean? Mutually disjoint means that out of these n subsets, if you choose any two, then they will have no common element, that is, they will be disjoint. So we write it like this. Generally we write AI intersection AJ will be empty for all ij. That means if you take, say for example, if I take any two, say A1 intersection A5, that will be empty set. If I take A5 intersection A3, that will be empty set, and so on. You pick any two, they will be their intersection will be empty. That is what we mean by mutually disjoint. And the second condition, exhaustive, that means if you take all the compartments, that is all these subsets, and take their union, then that will give you back the original set A. This is what we mean by mutually disjoint and exhaustive. So this interesting thing will happen automatically to the set A if you define an equivalence relation R on A. Now this phenomenon is called partitioning of a set. Partitioning of set A. So this is a new term for you, and probably this will not be given in your book, but you should know the term. So this is called partitioning of set A. Now one point you have to note here is important point is note this number, how many subsets, how many such compartments will be formed, that will depend on the definition of the equivalence relation R. So here number of such subsets that is, here I have denoted that number by n, depends on the definition of R. If you keep changing the definition of the equivalence relation R, then the number of such subsets, that is the whole partitioning of set A, will change. Okay. Now that you know what is partitioning of a set A, now I will come to equivalence class. Okay. So suppose small a is an element of the original set A. Then this small a will belong to some subset, of all the subsets that we have got, of them there will be one subset at least where this element will belong. So that subset, say let us take, say this small a element belongs to the subset, say A3. Suppose on inspection I find that small a is here, A3. Then A3 is called the equivalence class of the element A, and it is denoted by this symbol. That is, your A3 then becomes actually the equivalence class of the small element A, because it belongs to that subset. So you see, you pick any element from the set A, it will belong to some equivalence class or the other. Now the question is whether multiple elements will belong to the same class, or one element can belong to more than one equivalence classes or not. So that we will that I'll explain with the help of an example. So basically what happens is this equivalence class A will contains other elements of the set A also, but who are those elements which will all belong to A3? So this is how we define the equivalence class of A, that equivalence class of A will be the subset, or rather here let us say set, of all those elements of the original set A such that X is related to A. So whichever elements in the original set A are related to the small element A by the given equivalence relation R, they will all belong to this equivalence class A. So suppose you pick another element, say C. So let me, so suppose another element, let us take, say Y is an element of A. Then Y will also belong to this equivalence class if we see that Y is related to A. This is how we define equivalence class of an element of the set A. Now this will become very clear if I explain it with the help of an example. So we'll take a very classical example of an equivalence relation, which I'm sure you all of you know. So let's see which is that example. So let a relation R be defined on Z, that is the set of integers. So the set capital A that we had taken in the general theory above, that we are taking to be equal to Z. So a relation R is defined on the set of integers Z as R consists of all those ordered pairs AB such that A minus B is divisible by 3. So this is the particular equivalence relation we are taking. Now it's a different issue that to show that R is an equivalence relation, that will be in some other video that I'm not doing here. So for the time being, we assume that we know that this particular relation on Z is an equivalence relation. So then we know that R is an equivalence relation. We just want to see what is the type of partitioning that will happen to the given set of integers Z on which this particular relation is defined. Now before going into the partitioning, let me tell you one more thing. This particular relation, that is A minus B divisible by 3, then only that ordered pair belongs to R. This is also written as we write it like this: A minus B, or rather let me say that AB will belong to R if and only if A minus B is divisible by 3, or we write it like this: A equivalent to B modulo 3. This is read as this is the symbol we write, and we read it like this, that the relation is, this type of relation is called congruence modulo 3. So this particular symbol that I have written, this is read as congruence, let me write it like this: congruence modulo 3. So congruence modulo 3, that means A related to B or A equivalent to B modulo 3 means that A minus B is divisible by 3. Only then it will belong to the relation R. So this is just, these two are just alternative ways of saying, or rather I should say this is an alternative way of saying this same thing. So this term congruence modulo 3 is usually not written in the textbook. That is why I am giving you the information, but for the time being it is sufficient to know that A will be related to B if and only if A minus B is divisible by 3. Now let us see what happens to Z. What are the different subsets of the partition that will happen? Okay. Now the set Z, let me just write it like this. It is an infinite, so let me write it like this: minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, ... Okay, so this is Z. Now one by one let us pick up elements from Z and see which equivalence class it will belong to. So let us first take, say, let me name it number 1. So let us take the element 0. So 0 belongs to Z. So that means equivalence class of 0, that is the subset where 0 will belong, that will contain, according to the definition I had given earlier, it will contain all those integers from Z such that x is related to 0. That means what? This means all those elements that are related to 0 means all those x's in Z such that x minus 0 divisible by 3. X minus 0 divisible by 3 means x minus 0 is equal to 3k, where k is some integer. So that is what we mean by x minus 0 divisible by 3, that is x minus 0 is a multiple of 3, and multiple of 3 means 3k, where k belongs to Z. That means ultimately after simplification this becomes all those elements in Z such that x equal to 3k, where k is an integer. So this is, you can see, with the set builder form we have written the equivalence class. Now let us try to write it down in the roster form. That means actually list all those integers which will all belong to this equivalence class. Okay, now what is the value of k? K is an integer. That means it will take all these values written in red. So let us start from here and first take all the positive values. So suppose k is z. Let me do the rough work here for you. Suppose k is 0. In that case, x equal to 0. Suppose k equal to 1. So in that case, x equal to 3. Again, suppose k equal to 2. Then x equal to 3 into 2, 6. So this way it is going on, continuing in the positive direction. So let me write down 0, 3, 6. They will all come here. So 0, 3, 6. So you can already guess from here the pattern, that you are just simply adding 3 to the elements to get to the next element. So the next element will be 9, and then 12, and then 15, and so on. Now let us see what happens if k takes negative values. Suppose k is minus 1. So then x equal to k minus 1, so x equal to minus 3. K equal to minus 2, then x equal to minus 6. K equal to minus 3, then x equal to minus 9, and so on. So again you get the pattern. So I'm here, these dots are for all the positive values. So I'm writing the negative values here. So that means minus 3, minus 6, minus 9, they will all come here. So minus 3, minus 6, minus 9, and then how you are getting? See, minus 3, to that you add minus 3 to get minus 6. Again, minus 6 minus 3 is minus 9. So minus 9 minus 3, that will be minus 12, minus 15, and so on. So this is exactly the list of all those integers that will all belong to this equivalence class 0. That means if I try to draw the partitioning of the set of integers, so this was my initial set of integers z. So one partition we have already got, that is the equivalence class 0. And who are the elements? Of course 0 will have to be there, because that's the name, because 0 belongs to z and 0 is related to itself. This is an equivalence relation, so it is reflexive. So 0, 3, 6, 9 dot dot dot, minus 3, minus 6, minus 9 dot dot dot. So all these will go into the equivalence class 0. Now let us see which is the next equivalence class. So I have found actually the equivalence class of 0 first. Now I am going to the next one. I want to find the equivalence class of 1. So second is 1 belongs to z. So let us see which elements or which integers will be there in the equivalence class 1. So it will consist of all those integers such that x is related to 1. That means all those integers such that x minus 1 equal to 3k dash, because x minus 1 should be divisible by 3 according to the definition of the relation R. So I can write it is a multiple of 3, so 3k dash, where k dash is some integer. Now let us see which are the elements of z, or rather the integers that will belong to this equivalence class. Okay. So in the roster form we will try to list the elements. So what do we have here? Let me show the rough work here then. So x minus 1 equal to 3k dash. So that means x equal to 3k dash plus 1, where k dash is an integer. So now keep putting values to k dash and you get the corresponding values of x. So what are the values of x we are getting here? Suppose k dash is 0. So 3 into 0 plus 1 is 1. Suppose k dash is 1. So 3 into 1 3 plus 1 4. Suppose k dash is 2. 3 into 2 6 plus 1 7. And yes, you have got the pattern. 1 plus 3 4, 4 plus 3 7, and this way it continues. Now let's see what happens if we give negative values to k dash. So suppose k dash is minus 1. So if you put minus 1 here, this is minus 3 plus 1 is minus 2. So minus 2 will be here, one element. Now suppose k dash is minus 2. So 3 into minus 2 minus 6 plus 1 minus 5. And here also you can see this is the pattern. Minus 2 minus 3 is minus 5 minus 3. So that will be minus 8 minus 3 minus 11 and so on. So here is the total list of all those elements, that is all those integers that will all belong to the equivalence class 1. So just let's write them down. So the positive values are all here 1, 4, 7 and so on. So 1, 4, 7, and then you just go on adding 3. So 7 plus 3 10, 10 plus 3 13, 13 plus 3 16 and so on. And what are the negative values we found? Minus 2 minus 5 minus 8. So minus 2 minus 5 minus 8 minus 11 minus 8 minus 3 11 minus 11 minus 3 is minus 14 and so on. So that's equivalence class 1. So we have got another equivalence class here, which is equivalence class of 1, and all the elements belonging to this are 1, 4, 7, 10 dot dot dot, and then minus 2 minus 5 dot dot dot. So these are the elements in equivalence class 1. Okay. Now we suppose try to find the equivalence class of the next integer. So we have found for 0, we have found for 1. Now let us try to find for 2. What will be the equivalence class of 2? So again, as before, it will contain all those integers such that x is related to 2. That means all those integers such that x minus 2 equal to some multiple is x minus 2 is a multiple of 3. So suppose it is 3 k double dash, where k double dash is an integer. So you can see the process is same. So now that you have already understood, I will not go into the details of the rough work here. You can make it out what will be the elements that will be here. Let us do it directly in this definition of the relation. X minus 2 equal to 3k. So just let me write down that what is x? X equal to 3k double dash plus 2. So x equal to 3k double dash plus 2. So now if you put k double dash 0, what is this? 2. Now if the value of k double dash is 1, then 5, and as before you just go on adding and you get the subsequent elements. So 2 plus 3 5, 5 plus 3 8, 8 plus 3 11, 11 plus 3 14 and so on. Now let's see the negative values. Suppose you take k double dash as minus 1, so this becomes minus 3 plus 2, so that is minus 1. And then suppose this is k double dash is minus 2, so minus 6 plus 2, that will be minus 4. And so again, as before, same pattern. Minus 1 minus 3 is minus 4, minus 4 minus 3 is minus 7, minus 7 minus 3 is minus 10 and so on. So now we have got another compartment or subset which is equivalence class 2, and the elements are 2, 5, 8, 11 so on. Also minus 1, minus 4, minus 7 and so on. Now let us go to the next integer. So we have found for 0, we have found for 1, we have found for 2. Let us see. Now you will see an interesting thing will happen. Let us try to find out which elements or which integers are there in the equivalence class 3. So it will contain all those integers such that x is related to 3. That means x minus 3 is divisible by 3. So x minus 3 is multiple of 3. So suppose 3k1, where k1 belongs to z. Now again let us see which are the elements. So here we have x minus 3 equal to 3k1. So that implies x equal to 3k1 plus 3. So let's put the values of all the integers one by one to k1. So if k1 is 0, then you get 3. Then k1 is 1, you get 6. And if you keep putting the values, you will get all these values. Suppose k1 is minus 1, then it is minus 3 plus 3, so that is 0. If k1 is minus 2, then minus 6 plus 3, that is minus 3. And if you continue, you will get, and so on. Now do you see what has happened here? Equivalence class 3 and equivalence class 0, both of them have exactly the same elements. Can you see? Equivalence class 0 was, it had 0, 3, 6, 9, 12, 15. Same here, 0, 3, 6, 9, 12, 15, minus 3, minus 6, minus 9. So what do we see? Equivalence class 3 has become equal to equivalence class 0. What a surprise! So we are not getting any new equivalence class for 3. Now if you continue, you will see for all the other positive integers after 3, that is, say, equivalence class 4 will become, you can work it out yourself and verify. 3 has become equal to equivalence class 0, so 4 will become equal to equivalence class 1. 5 will become equal to equivalence class 2. 6 will become equal to equivalence class 3, which is also 0, and this way it will continue. Now see, till now I have been discussing only the positive, the equivalence classes of the positive integers. Now let us see what will happen to the negative ones. Already we have studied equivalence class 0. Now what will be equivalence class minus 1? Let us see. Already you know that minus 1, you can see that in the above listing, minus 1 already belongs to one of the equivalence classes, and which is that? Here you can see minus 1. It belongs to equivalence class 2. So let us try to find, already I have told you that an element, if it belongs to a particular compartment or subset, then that becomes its equivalence class. So since minus 1 is an element of the equivalence class 2, so equivalence class 2 is also the equivalence class for minus 1. So this is my expectation, that minus 1's equivalence class should be equal to the equivalence class of 2. As I can see, it belongs to this equivalence class. Now let us check it out. What is equivalence class minus 1? It will consist of all those integers such that it is related to minus 1. That means I'm not including the set format anymore. X related to minus 1, what does it mean? It means that x minus minus 1 is divisible by 3. That means it is some multiple of 3, where k belongs to z. That means what? X plus 1 equal to 3k and x equal to 3k minus 1, where k is an integer. Now this is the relation that will give me, or expression rather, that will give me all possible values of x's. Now k is an integer, so keep putting values. So suppose k is first 0, so what do you get? Minus 1. Then k is suppose 1, so 3 minus 1, 2. Then suppose k is 2, 6 minus 1, 5. Now suppose k is 3, 9 minus 1, so that is 8. So this way it is going on. So you can see the pattern, minus 1 plus 3, 2. So you just keep adding plus 3 to individual element to get to the next element. So minus 1 plus 3 will give you 2. 2 plus 3 will give you 5. 5 plus 3 will give you 8, and so on. So now suppose k is minus 1. So k minus 1 means minus 3 minus 1, so minus 4. And then k is minus 2, that is minus 6 minus 1, so minus 7. So yes, the pattern is again the same, minus 4 minus 3 is minus 7. So minus 7 minus 3 will give you minus 10. Minus 10 minus 3 will give you minus 13, and so on. So what we expected is actually true. See, the equivalence class of 2 contains all these elements: minus 1, 2, 5, 8, minus 1, 2, 5, 8, 11, 14, blah blah, and here minus 4, minus 7. So this is indeed equal to the equivalence class. So it is true. So this way it will continue. So what ultimately we see is, though there are infinite number of integers in Z, but the entire Z has been let me bring the picture here. Yes, so though Z is an infinite set, ultimately we see that there are only 3 compartments or 3 subsets into which this particular equivalence relation R has divided Z into, and they are equivalence class 0, equivalence class 1, and equivalence class 2. And after that you will get no new equivalence classes. So that is a very interesting thing that happens whenever an equivalence relation is defined on a set. Here I have taken the particular set Z because you are familiar with Z, but it can be any set. So ultimately that is the conclusion: any equivalence relation R on any set A partitions the set A, and the number of such subsets in the partitioning will depend on the definition of R. Here we have taken the particular congruence modulo 3 relation. So let me just show you once. We had taken this relation, congruence modulo 3. This was the name of our relation, that is A related to B if and only if A minus B is divisible by 3. So you can see why this number 3 is so important, because I have taken congruence modulo 3. That is why I have got 3 distinct subsets of Z. That is, I have got 3 equivalence classes. So if you redefine the equivalence relation R, say congruence modulo 5. So suppose you have like this. Suppose you define R like this, that R is a set of all those ordered pairs AB such that A minus B divisible by 5 instead of 3. So what will happen? Then Z will be partitioned into, then what will happen? Z will be partitioned into 5, exactly 5 equivalence classes. And they are, which are the classes? 0, 1, 2, 3 and 4. These are the only 5 different equivalence classes you will have. As soon as you go to equivalence class 5, you will get that to be equal to equivalence class 0. Equivalence class 6 will be equal to equivalence class 1, and so on. So these are the only. So what I said before, how many compartments or how many subsets into which the original set Z will be divided, that will depend on the definition of R, how you are defining R. So I hope you understood the concept of equivalence class. It is not explained in great length in the books, so I have tried to explain it in this video. If you think it was helpful, you could understand it, then please subscribe to my channel, and you can always let me know. You can write comments and give me your feedback, and also my mail ID is given in the description. You can send suggestions on topics on which you want me to make the video. So that's it. Thank you very much.